Today we're looking at Fourier optics, in my opinion, the only interesting part of optics. The reason I say that is because it has huge computational potential and it asks really interesting questions. For example, suppose I'm shining a light and I put a screen in the middle of the light so it's hitting the screen. So I know what the intensity looks like at that point. Fourier optics asks the question, what does the intensity look like further down? For example, it could go through lenses, it could go through slits. And the question is, after all these instruments that the light goes through, what does it look like at the end? In this video, I'm going to primarily deal with slits. So the question is, what is a slit? Well, I know that a slit is a little cutout of something, so I know that my light is zero everywhere, but it's, not zero at a particular place. But the question is, well, for a diffraction pattern, it needs to be a very particular type of slit. For example, if I just shine a flashlight through a hole and point it at a wall, I'm not going to get a diffraction pattern. I'm going to get just a little circle on the wall. For a diffraction pattern to actually occur, the slit has to be on the same order of magnitude as the wavelength of the light. And then you start to see diffraction patterns. As the name suggests, everything about the computation that we do is related to Fourier transforms. So if I know my initial intensity of light, for example, 0 everywhere except 1 in the slit, then I just do a bunch of Fourier transforms and I can compute what it looks like, as I move my screen farther away. The light goes through the slit, it starts doing weird things in space. I put a screen here and I get a weird diffraction pattern. We're getting fairly close to 10,000 subscribers, so if you enjoy this content, please subscribe and leave a like. Also, I've heard that subscribing to my channel has boosted people's IQ by about 20 points, so keep that in mind as well. Might come in handy for solving that difficult Lagrangian mechanics problem. So besides the typical NumPy and SciPy that we use, I have a number of libraries here for taking two-dimensional Fourier transforms and then also inverse Fourier transform. These are these two functions here. And then something called FFT freak and FFT shift. What this will do is when I have a Fourier transform of a function, and I know what it is in like the spatial domain, it will get me the corresponding frequencies in the Fourier domain as well. And FFT shift, you'll see, will come in handy. I have CV2 to open some images and then some matplotlib stuff to make animations. Another package I'm going to use in this video that I've never used before in past videos, it's called Pint, at least that's how I import it. And the way it works is that you can deal with units using this package. And so because I'm going to be dealing with like wavelengths that are nanometers, sort of slits that are millimeters, things that are meters, rather than keeping track of all these things, this package actually helps do that for us. So we don't need to be doing as many mental games as we're going through. And I sort of start it like this. So there's pint.unit registry. So I'll show you this. So I'll import the packages. And the way that the Pint thing works is I have this thing called U, and I have, for example, different units, so millimeter. And I can go like 2 times millimeter, 2 millimeter. I can also go like np.array, 1, 2 times millimeter, and it will actually form an array like this, 1, 2 with units of millimeter. So when I have arrays of different quantities and it will do math automatically, it makes this really helpful. So before I get into the coding stuff, it's useful to talk about the theory of Fourier optics, or scalar Fourier optics. So scalar Fourier optics considers a scalar function u of x, y, z, t that satisfies the wave equation that I have written here, and u squared is the intensity of the light. So the question is, what is this? Because we know that a light is an electromagnetic field that consists of vectors, an electric field vector and a magnetic field vector. So in some cases, U can be thought of as like the dominant component of the electric or magnetic field, so EX for plane waves. But in other cases, it's a little bit more difficult to interpret, and it's sort of beyond the scope of this video. And the main thing that you have to realize is that there's a quantity, a scalar quantity, that satisfies the wave equation, and its square is equal to the intensity of the light. And this exists at all points in space and time. So I can, look at a given time, what does the distribution of this scalar quantity look like in space? And as I square it, then I get the intensity of light at all points in space. Now we have the wave equation here for a light of a given frequency. I'm going to call it omega equals 2 pi f, where f is the Frequency, omega is the angular frequency, sort of use the same word frequency here. So it's monoenergetic, so you're sending light of a given wavelength somewhere. You look for solutions of the form u is equal to little u as a function of space here, e to the minus I omega t. So we plug this into the wave equation here, and you get the Helmholtz equation that looks like this. So if you substitute this in here, and you sort of take the derivative and stuff, you'll get this equation. And k is equal to omega over c, or 2 pi over lambda. So these are all the equations that maybe you're used to. So k is related to the wavelength of the light. And so this is the Helmholtz equation. And so we can find solutions to this equation by looking for separable solutions. So I say that my function u that solves it is a function of x times a function of y times a function of z. Now, the true solution for our particular problem won't be separable, but you can find a bunch of different separable solutions, add them together, and then you get your true solution. So separable solutions are almost like the unit vectors, if you're considering a vector space, and then you add up all the unit vectors in a combination to get your given vector. So I have my separable solutions, I get infinitely many of them, and then I can sort of sum them together to get any solution that I want. So I look for the separable solutions, the gradient looks like this. I plug us, which is this functions here, into it, and I get this equation here. And this is a trick that you might see if you've taken a partial differential equation course in the past. It's argued that each one of these must be a constant, because if this is a function of x, and I move everything on this side here to the left, then I have a function of x equals something that's not a function of x. So it has to be a constant. So each one of these fractions here is a constant. That gives me 3 equations that look like this. By the way, I'm going through this really quick. This is something that's typically covered in like months in a course. So I have an equation in x, y, and z for fx, fy, and fz. I can solve these equations, right? These are equations that you can solve. And it's just complex exponentials. That's like one type of solution to this equation. So it tells me that us, which is a product of fx, fy, and fz, each that are complex exponentials, looks like this. And I know that the sum of these k's, these are the constants that each of these are equal to, is equal to k squared. So I can take one of these k's and I can sort of write it in terms of the other two. So I take kz and I write it as k squared minus k squared minus ky squared. So that's my separable solution. And so there's any number, complex number a satisfies that equation. So to get the general solution, this is what our separable solution looks like. That depends on kx, ky, and kz, or just kx, ky, and k. And so there'll be a separate kx and ky for each of these separable solutions. And to get the general solution, you take a linear combination of all these separable solutions. And because there's infinitely many of them, we take this linear combination as an integral. So my integral looks like this. I sum over all the different values of kx and ky of us, the separable solutions. And so A will be different for each one of these solutions. Each solution is given by its kx and ky value. So I can say that A is a function of kx and ky, right? Because I can uniquely specify what A is for the given separable solution that is a certain value of kx and ky. So my A, I can just write it as a function of kx and ky. And then I plug in my separable solution that I found up here, right? And if you note that if you put in z equals 0, this is sort of the big trick behind all of this. If I put z equals 0 here, I find that this A, which is unknown to us before, you might be wondering what the heck is A. Well, A is the Fourier transform of u of x, y, 0. So if I'm shining light at something and I like take a cross section in z, and I know what the intensity of the light is there, I can find what my A is, and then I can use that to propagate and find what happens after that point as well. So this implies that A of kx, ky is the Fourier transform of u at z equals 0. That's just what this formula literally says in 2 dimensions, that A is the Fourier transform. So using f here, I write A is the Fourier transform of u of x, y at z equals 0. And so I plug this back into, or rather, I look at the original expression here that looks like this. For any value of z, this isn't z equals 0, this is any value of z. And you'll note that this itself is an inverse Fourier transform of A, kx, ky, times this quantity here. So this whole thing, this is an inverse Fourier transform because I'm taking the integral and I'm multiplying it by this. So in general, u of x, y, z is the Fourier inverse of A of kx, ky times this quantity here. And a of kx, ky is just the Fourier transform of u. So it provides a really elegant way to find what u of x, y, z is. I take the Fourier transform at u at x equals 0. So I take a cross section of my light, right, at z equals 0. So for example, this might be light going through a slit, and I know that the light is confined to that slit. So my cross section is 0 everywhere and at the slit. And then as z goes, the question is what happens to the light after that point? And so I can find what a of kx, ky is. And if I want to find what it is at any value of z, so as I move sort of through the slit and beyond that, I just take the inverse Fourier transform of a, which I solved up here, times this quantity here. And I choose the minus sign, by the way, because you'll note that I have a plus or minus iz. I choose the minus sign here because we're considering waves moving through the slit in the positive z direction as opposed to backward. Because you'll note that if I just know the intensity through the slit, the question is it coming through the slit or is it going, which way is it going? So taking the negative sign, I sort of decide that convention that the wave is moving through the slit. And so, yeah, these two boxed equations, you can find the intensity of light at any point, provided you know it at a given cross section in Z. And so the important things to note here, the things that are unknown, is K is related to the wavelength of the light. K is equal to 2 pi over lambda up here. And u of x, y, z equals 0 is given by the distribution of light, say as the light is going through a slit. So that's like, it could be a little box of light, right? The intensity is here, and then it's blocked by the screen. And the question is, what happens to the light after? And so you might see now why it's called Fourier optics, because it's all related to Fourier transforms and inverse Fourier transforms. So we'll do a few experiments just to confirm that what we're doing is indeed correct, and then we'll do some cooler animation stuff. So we'll start with the single slit experiment. So capital D here is the slit distance. D is 0.1 millimeters. And the wavelength I'm going to say is 660 nanometers. So again, this package is new in my videos, but you'll see that it defines it specifically, and it's got the unit as well, so that you'll see how this will make things easier. So I'm going to define the spatial grid, and then I'm going to define the actual slit as well. So x, this is sort of the unit dimension. It's going to be 2 dimensions, right? So there'll be an x-axis and a y-axis. They're both given by this, it goes from -2 to 2 millimeters in 1600 steps, all in units of millimeters. And then I make a mesh grid of x so that I have sort of that 2D thing that I can plot. So now I define what my intensity of light, or rather the square root of the intensity, because this thing squared is the intensity. I define what this looks like at z equals 0. So I say where x is less than d over 2 and y is less than 0.5. So my width is d, but the absolute value is less than d over 2, means it goes from negative d over 2 to d over 2. And then y, it goes from negative 0.5 to 0.5. So it's a 1 millimeter height slit and then d width of a slit. And I turn this into floats because this, of course, is going to be Boolean, right? Because this is a Boolean operation. And so this turns it into float. And you'll see exactly what I mean. If I go like this, it returns an array of Boolean quantities here, false. And then there'll be a little bit of trues in the center where x is less than d over 2. And the same thing for y here. This gives me all the y values, and it will be equal to sort of 1 millimeter. It will be true in the center. So now that I have u, I can plot what it looks like, and I'm using my mesh grid that I created, and I'm using the value of u that I have as well. And so it'll plot, and you'll see that my slit just looks like this. So I have 0 everywhere, and then the light is shining through the slit at z equals 0. So this is exactly what I want. I want it equal to some quantity here. I think it's just equal to 1 because this was Boolean. So it's equal to 1 here and 0 everywhere else, right? So that's what my light looks like initially at z equals 0. The question is, as I go through the slit and the light sort of propagates through, what happens to it? And you'll, as you know from first year physics, you get a diffraction pattern on the screen, and that's related to these two equations here. So there's 2 equations that I mentioned above, and the first thing we need to do is get a of kx, ky, given by this boxed equation up here. And for that, I need the Fourier transform of u. So I take the 2D Fourier transform of u naught, that's z equals 0, and then I get my Fourier frequencies as well. So what I do here, this is a little bit confusing, but you'll note that FFT freq, this gives me my Fourier frequencies, and x is my sort of points in y, right? And so if I just look at this, these are my frequencies in units of 1/millimeter. And I specify the length of x, because however many points there are in x, there's going to be that many Fourier frequencies. And I also give the spacing in x, right? I know that my spacing is 0.0025015 millimeter. And that's how you can compute what the Fourier frequencies that the computer's computing. If you're confused about this, I would highly recommend checking out my Fourier series video that I have on my channel as well. So this will give me the Fourier frequencies, and I need them in 2 dimensions. Oh, and I need them in angular frequency, because that's what we're considering. And this gives it in true frequency. Multiplying by 2 pi gives it to you in angular frequency. And then afterwards, I create a mesh grid so that I can do some plotting. So now that we've computed a, kx, and ky, I can plot the Fourier transform, which is what I do here. And you'll note that I'm doing an FFT shift here. And this is because in Python, when you take the Fourier transform of something, instead of dealing with only positive frequencies, it does positive and negative frequencies. If you only want to deal with positive frequencies, and this is said very simply, it's a little more complicated than that, but if you only want to deal with positive frequencies, you have to make sure that you use FFT shift to shift everything. So you're not dealing with positive and negative, you're dealing with positive and positive. This has to do with like sampling theories and things like the Nyquist frequency, and the fact that the Fourier transform is repeated over and over. It's a little complicated, but just always use the FFT shift, especially when you're doing 2D transforms, because otherwise the 2D thing that you plot doesn't really make much sense. So this is why I imported this function. So now that we have the Fourier transform of our thing, we need to write the function that returns u of x, y, z. And of course that's given by this equation here. So we have a of kx, ky. Now we need to take the Fourier inverse of this multiplied by this. And I have kx and ky as a mesh grid. So this is a 2-dimensional thing. And because kx and ky are mesh grids, they're each 2-dimensional as well. So that I can plug in all my NumPy arrays in here and I get a 2D array that I then take the inverse 2D Fourier transform of. So that's exactly what I do here. I have my inverse 2D Fourier transform. I have a, which is what I found by taking the Fourier transform of u naught. I multiply this by that exponential of k squared minus kx squared minus ky squared, all square rooted. And then I also have z as well. So I plug in whatever value of z I want. So however far away the screen is from the slit that I'm doing the diffraction experiment on, and k, which is related to the wavelength of the light. So this is a function to get u at any value of z. And I can specify the distance of the slit to the screen, z, which is equal to d, little d, that's typically the convention that's used in the single slit experiment, and k, which is just 2 pi over lambda that I defined before. So I have k and d, and I can use this to get u here. And by the way, these little errors here, these have to do with the units package, and it's because it's stripping the unit sometimes, and it's just something that shows up. So I plot what u looks like, and I indeed have my diffraction pattern here. You can see that there's the central thing, and then these things sort of going off like this. And I want to confirm that the results are actually precise, like I'm getting the right thing, because it looks right. The question is, are the minimum where they're supposed to be? So for the single slit experiment, the minimum of intensity occurs at angles theta, such that d sine theta is m lambda. That's something learned in first year. And sine theta is equal to x over x squared plus d squared. So x is if the screen's like this, x is the distance on the screen, and d is the distance from the slit to the screen. So I can find what theta is using x, and this is the hypotenuse. Sine theta is equal to opposite over hypotenuse. And then I can solve for x, and I get my values of x like this. So it's m lambda d over d squared minus m squared lambda squared. So I plug in a value of m, and it gives me all my different values of x's where the minimum should be. And I know what lambda is, I know what d is, the distance from slit to screen, I know what capital D is, and I just give a bunch of different integers for m, and then I get all my positions of my minimum. So here I have m from 1 to 5, and I get my values of x, and I can plot vertical lines at these minimums. So by the way, I'm taking the magnitude of x, because of course this is going to be unitful. If I look at x min, for my package that I have, these are in units of millimeters. So if I take just the magnitude, it will sort of strip the units from it. So that's really useful when plotting sometimes using this package. So I have the positions of the minimum, and I just give these dotted red lines, and I plot x and u, and you can see that my diffraction pattern, by the way, I take this value in the center, so I'm just taking a central slice here of the diffraction pattern, and you can see that my diffraction pattern looks like this, what you would expect to see in the single slit experiment, By the way, if I want the actual intensity, I would need to square this. I sort of choose not to do this because you get rid of the bumps a little bit. If I take the square root, you can sort of see it a little more exaggerated. And you can see that these dotted lines do indeed lie at the minimum. So whatever we're doing here with Fourier optics gives results that we expect. And so for the future experiments, I'm just going to write a function that does everything automatically. It takes in your initial slit or initial intensity of light, or the slit or whatever, xv and yv, which are the position. It takes in the wavelength, and it takes in the value of z, sort of the distance from the screen to the slit. And it just does everything that we've done automatically here. So the next interesting experiment is the double slit experiment. And this is one of the most famous experiments ever in physics, especially because of the quantum phenomenon that occurs in this experiment. But this isn't what we're considering here. We're just considering classical light mechanics here. So here I define the distance between the slits, little s, so that's 0.2 millimeters. The slit width, capital D, is 0.05 millimeters. And I'm going to use that to get the initial field. So I define my spatial mesh grid like I did before. Here it goes from -4 to 4 millimeters, 3,200 different points. I create my mesh grid. And then what I do to get my I want two slits right next to each other. And so I say where x minus s over 2 is less than d over 2, yv is less than 2 millimeters, x plus s over 2 is less than d over 2, and y is less than 2 millimeters. And so this gives me one slit, and this gives me the other slit, right? So this gives me something that's centered at -s over 2, and it's sort of a width d, and then y is 2 millimeters. And so I multiply these together. So this is, and you need this and this to be true. I need this and this to be true for the other slit. And then I take an OR. A plus is equal to an OR when you're dealing with Boolean stuff, right? And remember that each of these is a Boolean array. So if I take y is less than 2 millimeters, I get this Boolean array that looks like that. And so this is what my initial, I'm dealing with a Boolean array for each 4 of these things, and then these are Boolean operators. Then I convert it to float, so the value is 1 everywhere. And I can show what the initial field looks like. And I get something that looks like this. I have my 2 thin slits right next to each other. The question is, what does the resulting field look like? And so I use my compute function that I wrote before, and I can plot what the diffraction pattern looks like. And lo and behold, you get the double slit pattern that you expect. You get this sort of big, bright, intense pattern in the center, and these lighter sort of things going off. And then also within each sort of bright packet of light, you get these oscillating pattern as well. So that's the classical double slit sort of thing that you expect. So a little more obvious, we can look at like a central slice to actually look at the magnitude of things. So I'll take the central line sort of cutting right through here, and I can plot what the field looks like. And of course, this is the double slit intensity. So I have my main sort of lobe. I forget what they call them in first year. It's some sort of lobe or whatever. And then you also have the little oscillating within each lobe. And you can see a lobe here, a lobe here, a lobe here. It's not like infinitely precise, but it's doing sort of the right thing. So you can see with Fourier optics, you have to be very careful with how you define things in order to get a result that looks decent. Because a lot of times, if you create the dimensions wrong or whatever, there's a lack of precision that occurs when you're dealing with these numerical Fourier transforms. So this is a particular case where it works well, but it doesn't mean that it always gives the correct result. So we can also do this for a circle. Here I'm just saying my radius of the circle is 0.1 millimeters. I create my initial pattern like this and compute the value of u. And the question is, if I have a little circle of light and I put a screen back, what does the pattern of light look like far from the slit? So I have a slit here, the light shines through the slit, and then I have a screen here. It's a little circle that the light goes through. What does the light look like when it hits the screen? Well, you get the center portion here, and then you get these sort of radial outward lobes. I don't know if you can see that. Hopefully the video quality is good enough, but it sort of oscillates like this. So it's a weird thing. It's a diffraction pattern. As you shine light through, because it interacts like a wave, you get these sort of wave-like things that appear on a screen. So finally, we can do an experiment with different wavelengths of light, and we can ask what happens as I shine different wavelengths through a slit. And so I'm going to shine it through a hexagon slit here. And so I do a little bit of stuff here to interpolate the image and make it the correct size. I want it 1600 by 1600. These 3 functions do this. And then I get my initial intensity of light like this. So for example, if I just run these cells and I look what U0 looks like, it's just a hexagon like this, where it's 1 here and it's 0 everything else. And the diffraction pattern for this hexagon slit is really cool, by the way. So I can get rid of this, and I run this cell, I get my value of U0. I have 4 different wavelengths here of 400, 500, 600, 700 nanometers. These are all in the visible spectrum. And I create my spatial grid like I did before, and I'm going to compute U for all these different wavelengths. So I have 4 different wavelengths. I have my slit. The distance between the slit and the screen is 6 centimeters in all these cases here. And then the question is, what does the pattern look like on the screen for different wavelengths? Now, I want to actually plot the right color here. So I found this function online. It's called wavelength to RGB. Of course, color on a computer is RGB. That's like an array of 3 different values that gives a red value, green value, and a blue value. And I don't know exactly how this works. And again, it's sort of beyond the scope of this video. But what it does is it takes in a wavelength. It's a function that takes in a wavelength. It's got this adjustable parameter gamma here. And it will return the value of R, G, and B for each wavelength. And there's got a number of cases here for different wavelengths. But I give you a value of a wavelength, and it returns RGB that gives a color on the computer. And so I can use this function then to create color maps for each one of those wavelengths that I have. So I have 4 color maps here. Probably shouldn't call this custom red. I could just call it custom for each one. And it goes from 0, 0, 0, so black, up to the color RGB for that given wavelength. So it takes my wavelength to RGB, and I'm giving it the value of lambda. And that's 256 values in this color map, and I'm doing it for all 4 color maps here. So this list that I'm defining here, it's list comprehension, I have for 4 different values of lambda. And so I can index C maps to get my color map for each of the 4 wavelengths. So I've solved for all my different values of U nu. I have my color maps, and I can plot what each of these looks like. And now here's the interesting thing that you might notice. For the smaller wavelength, when the wavelength is small compared to the slit, you get no diffraction. As the wavelength becomes much, 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 much smaller than the slit, you don't get any diffraction happening. It's like shining a flashlight through a hole, right? You're not going to get a diffraction pattern on the screen. The reason for that is because the slit is much bigger than the wavelength. So for 400 nanometers, small wavelength, you get some diffraction, but not as much as 500, 600, and 700. The larger the wavelength compared to the slit, the more diffraction that you get. This is how sort of light and waves work when they're passing through, like a slit or something like that. And it's really cool what it sort of looks like here. And so I have some function here that can turn this into an animation. And so it's really cool because you can make an animation of what happens as the screen becomes farther and farther away from the light. And you can see it sort of diffracting as it gets farther and farther away. Of course, initially it looks like just a slit, and then it starts diffracting more and more as you get away. So I'll show you that animation now. So here you can see it starts as a hexagon, and as it starts diffracting more and more, you get this diffraction pattern coming out from the sides. It starts doing a really cool sort of diffraction pattern in the center. And of course, as the time goes in this animation, it's as if you're moving the screen further and further away from the slit. So it starts normal, it starts looking like it does in the slit, and then as it gets farther and farther away, you get this diffraction pattern that's occurring. Anyways, I hope you enjoyed this video. If you want to see more stuff in Fourier optics, please comment and let me know, because there's a lot of cool paths that I could potentially take on this channel looking at various problems in Fourier optics. For example, here we only did monochromatic light. There's also the case, well, what happens if you shine a white light through a slit? Well, then the different wavelengths diffract differently, and you get really cool looking diffraction patterns that way. So that's a possible option for a future video. Anyways, I'll see you next time.